Is it possible for a calculated or estimated answer to be good enough? This is the question that students will explore in Investigation 2A, Indirect Measurement, Estimation, and Scale. In Investigation 2A, your students will practice making indirect measurements and estimations and compare their answers with other students' answers. Through their experience, students should learn that in science, indirect measurements and estimates can provide the best answer to our questions. For this investigation, each student group will need a metric ruler, a ream of paper, a balance, some rice, a meter stick, and you might also want a protractor and a measuring tape. What is the mass of a grain of rice? How thick is a sheet of paper? How tall is a tree? In Part 1, students will work together to answer these questions and then compare their answers. To find the mass of a grain of rice, students can count and measure the mass of a number of rice grains, and then divide the mass of those grains by their quantity to find the mass of a single grain. Here I have 140 grains of rice. Using a balance, I found their mass to be 3.2 grams. If we take the 3.2 grams and divide by the 140 grains of rice, we find that the mass of a single grain of rice is 0.023 grams. Students can find the thickness of a single piece of paper by measuring a ream of paper and dividing by the number of sheets in the ream. As you can see, this ream has 500 sheets. I unwrapped a ream of paper and measured it using a metric ruler, making sure that I used the centimeter side. I found the height of the paper to be 5.3 centimeters, or 53 millimeters. I divided the height of the paper, the 53 millimeters, by the 500 sheets and found that the thickness of a single sheet of paper is 0.106 millimeters. One way to find the height of a tree is by using its shadow on a sunny day. If we measure the shadow of a tree, we can compare it with the shadow of a meter stick that is near the tree. The ratio of the height of the meter stick to the height of its shadow is the same as the ratio of the height of the tree to the height of its shadow. Since the meter stick is 1 meter long, we have measured the shadows in meters, and the height of the tree equals the ratio of its shadow in meters to the shadow of the meter stick. Students who know trigonometry can figure out how tall the tree is without using the sun. If we want to find the tree's height, we can choose a spot on the ground, some distance from the bottom of the tree, and we can use a protractor at that spot to find the angle between the ground and the treetop. If one student holds the protractor and adjusts the meter stick, their team can coach them to align the meter stick so that it points to the top of the tree, and then they can read the angle. By using the angle measured on the protractor and measuring the distance from the spot to the trunk, the ratio of the height of the tree to the distance from the spot to the trunk will be equal to the angle, the tangent of the angle that was measured on the protractor. And then the height of the tree can be found with the distance from the spot to the trunk times the tangent of the angle theta. We found it difficult to correctly measure the angle by pointing the meter stick at the top of the tree. By taking a photo of the tree and the student holding the meter stick at the spot that we measured from, we were able to measure the angle from that spot to the top of the tree on the picture and get a height for the tree that matched the height that we estimated using shadows. Students should record their values for questions A, B, and C in Table 1. In this table, each row contains the data for a separate lab group. Your students will calculate the average value and the standard deviation for each activity, and then explain how well their lab group's answers agree with the class average. In our case, the mass of a grain of rice turned out, on average, to be 0.023 grams, and the standard deviation was fairly small. The thickness of a grain of paper we measured to be 0.107 millimeters. You might find something somewhat close to that. The height of a tree. Now, this is going to depend on your tree, but ours came out to be just shy of 8.5 meters, with a standard deviation of approximately 13 centimeters when you measure it out. Now, the standard deviation is an indication of precision, and it tells how close the data points are to each other. Our data could be precise in that we have all measured similar values without being accurate. Our tree, in particular, was a little bit lopsided, and the highest clump of leaves that we measured was not directly over the base of the trunk, so our measurements of the shadow could have been off by 10%. But without climbing to the top of the tree with a measuring tape or bringing a ladder, we got a height for the tree that should be accurate to within 10%. For our purposes, that is good enough. In Part 2, Question A, the mass of a single atom of gold can be found from the mass of a mole of gold atoms, as given in the periodic table. A mole of atoms contains 6.02 times 10 to the 23rd atoms. Since the mass of a mole of gold is 0.197 kilograms, the mass of a single gold atom can be calculated using the number of atoms in a mole. The mass of an atom of gold is 3.27 times 10 to the minus 25th kilograms. For Part B, the number of gold atoms in a 1 meter cube can be calculated from the density of gold and the mass of a single gold atom, which we calculated in Part A. Since the density of gold is 19,300 kilograms per cubic meter, and we calculated the mass of a single gold atom to be 3.27 times 10 to the minus 25th kilograms, we can calculate the number of atoms in a cubic meter of gold to be 5.9 times 10 to the 28th atoms per cubic meter. In Part C, if the gold atoms are packed together as shown in the picture, the diameter of a single gold atom can be calculated from the number of gold atoms in a cubic meter. First, we calculate how much space a gold atom takes along a line by taking the cube root of the number of atoms in a cubic meter. This gives us the number of atoms along one side of a cube a meter long. We find it to be 3.89 times 10 to the 9th atoms along a side. The diameter of one atom will be 1 meter divided by the number of atoms along a meter. So we find that the diameter of a single atom of gold is 2.57 times 10 to the minus 10th meters. In Part 3, to compare different amounts of time, we have to make sure that all of the times that we are comparing are measured in seconds. In Part A, to compare a year with 100,000 seconds, we first need to find the number of seconds in a year. We know that a year has 365 days, that there are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. When we calculate the number of seconds in a year, we find that we have 3.15 times 10 to the 7th seconds in a year. Comparing this with 100,000 seconds, we find that 10 to the 7th is greater than 10 to the 5th. In Part B, students can Google the number of times that a mosquito flaps its wings in a second. The numbers that I found are between 500 and 1,000 times per second. An hour has 3,600 seconds. The hour is larger than the number of times that a mosquito flaps its wings. in a second. In part C, the time for one oscillation of the quartz crystal in your watch is approximately 3 times 10 to the minus fifth seconds. A millisecond is 10 to the minus third seconds. The millisecond is greater than the time that it takes for the quartz crystal to oscillate in your watch. In part D, students compare the time between their heartbeats with the time that it takes for a pencil to hit the floor falling from a desk. An adult's resting heart rate is between 60 and 100 beats per minute. A single beat could be between 0.6 of a second and 1 second. We can use the equations of motion to find the time that it takes a pencil to hit the floor. The position of the pencil is equal to its initial position plus its initial velocity times time plus 1/2 times the acceleration times the time squared. The pencil starts from rest, so that means that the initial velocity is 0. If we assume that the desk is 80 centimeters tall, which is about 31.5 inches, then that means that the distance that it falls is 0.8 meters. We want to put this information into the value that we found for time, which is twice the distance that it falls divided by the acceleration. We're going to use the acceleration on Earth, which is 9.8 meters per second squared, which gives us for the time 2 times 0.8 divided by 9.8, 4/10 of a second. So that takes 4/10 of a second for your pencil to fall on the floor, and we're going to compare that with a heartbeat. Well, looks like it takes longer for your heart to beat than it does for a pencil to fall to the floor from your desk.